So we finally reached the topic on differentiation. And we have looked at differentiation in IGCSE previously before. And we're going to explore all the many ways that we can differentiate all different types of functions. But before we do that, it's important that we understand where the idea of differentiation came from. So differentiation forms part of something that is called calculus. And calculus is simply what we would say is the study of change, right? And calculus is made up of two important parts. The one, which we're going to look at now, is called differentiation. And the opposite of differentiation is something that we call integration. And that's something that we'll look at a little bit later on. So let's think about what differentiation is. And to understand that, we need to understand what change is. Now, in maths, we know that change is when one quantity could change in relation to another quantity. And we've studied this many times before when we've considered the gradient of a straight line graph. So if we had a straight line graph y equal to mx plus c is the y-intercept and m is the gradient of the straight line. And we should know that the gradient of a straight line is y2, y1 over x2 minus x1, right? In other words, it's the change in the y value divided by the change in the x value, right? And the wonderful thing for us that we know is that the gradient of a straight line is the same at any point on the line. Right? Now, if we look at the formula for calculating the gradient, we'll notice that we have two y coordinates and two x coordinates. And that kind of brings about this fundamental idea of change. If you want to calculate the change in something, you need to know two things about it. Right? If you don't know two things about something, it's difficult to understand what has changed. So in order to calculate the gradient of a straight line graph, we would need 2 points on the graph. Now, when it is a straight line, that's no problem. We can identify 2 points, we can calculate the gradient, and we know that at any point on the straight line, no matter where we are, the gradient at every point on the straight line is exactly the same, or what we would say in mathematics, it's constant. Now, if we move on and we have a look at this graph here. Now, it doesn't really matter what this graph is. The important thing to notice is that it's a curve. And if the gradient measures the way that the line is changing, we'll notice that the gradient at every point on the curve is different. Down towards the bottom, the gradient is very shallow. There's very little change. And as the gradient, or as the x values increase, the gradient of the graph is increasing. It's getting steeper and steeper and steeper. And so every point on this graph, the gradient is different. Now, we learned back at IGCSE, the only way we could calculate the gradient is by approximating a tangent at a specific point. So we could draw a tangent as close as we could to a single point, and that would best approximate the gradient of the curve. Now, the reason we had to do that is because in order to calculate gradient, we need 2 points. So we would have to take 2 points on the curve. And if we join these points up, we notice that the points that we've selected don't accurately describe the gradient at a specific point. It's slightly off. And so the only way we could do this was by approximating the gradient at a specific point on the graph and calculating the gradient of the straight line and then using that value. Now, this is fine if you need to calculate the gradient once. It might not be accurate, so depending on the application, if it's useful or not. However, if we want to calculate the gradient at any point on the graph, well, you can see that this becomes a problem because now we need to draw a straight line every single time that we want, or tangent every single time we want to calculate the gradient. So if we need 2 points in order to calculate change, that poses a bit of a problem. because if we need 2 points, we can never draw a straight line that will best approximate the gradient of a single point. And this idea troubled mathematicians for many years, until almost at the same time, 2 mathematicians, Leibniz and Newton, had the idea that we can't calculate the gradient of a single point, but what we can do is we can look at what happens as we start slowly approximating a gradient that is closer and closer and closer to the gradient of a single point, right? And they came up with this idea of limits. So we can look at the limit as the line that we draw tangent between 2 points. So in other words, what we're doing is we're selecting 2 points that are closer and closer and closer and closer and closer and closer and closer, and we're looking at what is the limit as these 2 points approach each other and basically are on top of each other. We can't obviously have them on top of each other, but we're looking at what would happen if they could be on top of each other. And so we came up with this idea of a limit. So once limits were discovered, we were then able to better come up with an idea for calculating the gradient for a single point on a curve. And this is where the concept of differentiation evolved. So what we're going to do is we're going to calculate the gradient function, right? And we're going to discover where it comes from. So what we're going to do is we have this function f of x. It could be any function, it doesn't matter. And we're going to select a point on the function, right? And this point, it doesn't really matter what it is. Its value would just be x. Now, if we stuck f or x into the function, right? So if I put x into f of x, well, if I put x into f of x, what will come out is f of x. I'm putting x into f of x. And what we can do is we can select another point on the graph. So we can select this point here, and we're going to select this point, and we're going to call this point x plus h, because we want the distance between these 2 points to be exactly h units. Okay, and h is just the convention. It could be anything. So if we want the distance between the 2 points to be h, then the point that I've selected on the graph must be x plus some small value for h. Okay, and if I put x plus h into f of x, right, its corresponding y value will be f of x plus h using function notation. Okay, so now I have 2 points on the graph and I know what they're called. So now I want to calculate what the gradient is. So we know that the gradient, right, the gradient is equal to change in y over change in x, all right? And so what I want to do is I want to take my change in y. So the change in y is the difference in the y coordinate. So here we have f of x plus h, and we want to subtract f of x. Okay, so that's the change in y. And we're going to divide that by the change in x. Now we decided what the distance between those two x coordinates were going to be. It's just h, right? We defined that when we set up the second point. So here we have the change in the y coordinates divided by the change in the x coordinates. However, these 2 points are not on top of each other, they are separated. And so we aren't accurately approximating the gradient at a single point. And so what Leibniz and Newton said, well, what we'll do is to calculate the gradient, we'll take the limit, okay? What's the limit as h approaches 0? In other words, I want to make this change so small that it's almost 0, right? So what's the limit as h approaches 0 of this f of x plus h? minus f of x all over h. And so what they came up with, this thing that you see in front of us, is what we call the first principles of calculus, right? So if we want the gradient function, and we're going to learn about notation in a minute, but the gradient function f dash x, right? In order to calculate a function that describes the gradient, we can take this change in y over change in x as that distance between the 2 points approaches nothing, right? So the limit as h approaches 0 of f of x plus h minus f of x all over h. And this is what we call the first principles of calculus. Right? It was a defining moment in mathematics when Newton and Leibniz came up with this idea of limits to allow us to calculate the gradient of a single point by looking at what the values approach as the distance between the 2 points becomes 0. So before we look at how first principles works, we can just quickly look at some of the notation that's important when we are dealing with calculus. Okay, so we differentiate, right? Differentiate is the noun or the verb. It's the doing. When it's the doing thing, we're differentiating, and when we differentiate, we calculate something called the derivative, right? Or sometimes known as the gradient function. Okay, depending on what the notation or what the expression looks like. Okay, so for instance, if I have some equation y equal to some value of x, right? We've already previously seen that its derivative is what we call dy on dx. That would be the derivative, okay? And d is for delta. Delta is the Greek letter for which is a representation of change. So that's change in y over change in x, which is exactly what we calculated. Right, another way we can write the derivative is if we have a function of x, then when we differentiate it, we get something called the gradient function, which we call f dash x, not to be confused with f to the minus 1x, okay? So f dash x is the first derivative of f of x. However, we don't just have to differentiate equations, all right? So y equal to x is an equation. F of x, a function of x, is generally an equation expressed as a function of x. We can also differentiate just expressions. So if we just have an expression with x in it and we differentiate it, then we call the derivative d by dx. We're differentiating x with respect to itself. Okay? So when we differentiate, we're always differentiating with respect to some variable, because we don't always have x and y. Sometimes we have v and t or s and t, depending on what formula we're using at the time.